Now I want to talk about memory graph neural networks, which has a lot of citations because it's very important. This is the anatomy of our memory in our mind. Our declarative memory is on our temporal lobe, and neocortex is used for perceptual learning. Striatum is used for skills and habits. Of course, it's just a simplification. Amygdala is used for emotional. So there are different long-term memories, declarative and non-declarative in your brain. So I have written more than 3 articles about this hippocampus and also prefrontal cortex, which is the integrator of everything. All of the information comes. It's like a computing reservoir. So it's your computing reservoir. And then the input is your hippocampus. And so there is no striatum here, but striatum is here. It could be the output, it read out of what you're understanding. Of course, you can see that semantic parsing is here. And this, for example, data comes from back of your mind, visual cortex here. And so everything is connected with some models that I model it with reservoir computing, and I connect these modules to each other. So I model all of the brain with some modules, just like control systems, that some modules to define and explain each part of the brain. And if you simulate like this, then you can create a new machine, much more important than classical artificial intelligence. Because you are using asynchronous networks, you are using, for example, when you are using this reservoir computing, it's very biological. So I want to explain this article in 2020. Graph neural networks are a class of deep models that operate on data with arbitrary topology. We can introduce an efficient memory layer that can jointly learn node representation and coarsen the graph. So your graph is very complicated. We are trying to coarsen it. I have an article in Math Archive probability, that I showed how you can do entropy maximization to do that. So the memory layer is like here. We define this memory layer as a parametric function that takes queries of size DL and generates NL plus 1 query vectors of size DL plus 1. The input and output queries represent the node representation of input graph and the coarsened graph. So in a content addressable memory, I've explained Alex Graves' articles in the previous lectures. The task of attending to memory addressing scheme is formulated as computing the similarity between memory keys to a given query. So it's just like the idea of neural Turing machine, and after that, differentiable computers in DeepMind. So all of them are the same until here. The soft read operation is defined as a weighted average over the memory keys. So these are memory keys, just like previous lectures. But now they are doing something interesting. They are normalizing the similarity. They use this similarity for some kind of KL divergence between, so it's a kind of unsupervised learning. It's very interesting. So as a node, so we treat input queries as a node representation of an input graph, and treat the keys as the cluster centroid. These are centroid. And they use student t-distribution as a kernel measure to normalize similarity between this query and the keys. So think about it as a probability. And the aggregated soft assignment matrix is just the soft max, and you're concatenated, of course, all of them. Concatenate all of them. And CL is the aggregated soft assignment matrix. But a memory read generates a value matrix, this one, that represents the quotient node representation in the same space as the input queries. And so you are quotienting your graph. You can read about it on this article. The value matrix is fed into single-layer feed-forward neural network to project the quotient embedding. So sigma here is the nonlinearity, it's just a leaky ReLU. And the rest is simpler. You just, for graph classification, for example, for this task, you can simply stack layers of memory up to the level where the input graph is coarsened into a single node representing the global graph representation, and then feed it to a fully connected layer to predict the graph. So unlike the previous lectures, the query network in MEMGNN relies they rely on message passing to compute as follows. But in an EGAT layer, attention score is computed like this. So for training, they use supervised loss, but with the unsupervised clustering loss. Here they use KL divergence, like here. Because they know the target distribution. There is an article that introduces by Farhadi, I guess, that introduces this nice target distribution. So it's totally unsupervised. But if you minimize the KL divergence between target distribution with what you assigned, your self-assignment, then you augment it with the supervised learning and unsupervised learning, it becomes a total loss. So total loss is here. Sometimes you have some supervised loss and you have some unsupervised loss. Depending this hyperparameter lambda, you can say which one is more important. You can have different values. And if you want, that is the article of Ali Farhadi, and that they introduced this target distribution. So if you want to know that, to see the roots of that, you can read this article. And she is an amazing scholar in University of Washington. There are many genius people in University of Washington and Carnegie Mellon and Stanford. Because whenever I read their articles, I understand it's very interesting. I don't know why it is so interesting and elegant. We initialize model parameters, the keys and the queries randomly, and optimize them jointly with respect to L using mini-batch stochastic gradient descent. To stabilize the training, the gradients are backpropagated batch-wise, while the gradients are applied epoch-wise by periodically switching between 0 and 1. The datasets that they use are, for example, for proteins, to predict the protein function from this structure.